Hi, everyone. Let's talk about the graph of an equation in general, and then go on to circles, some very basic graphs. The basic principle of graphing. This may be obvious to some of you, but actually it's a lot deeper than you might think. The graph of an equation consists of all points whose coordinates satisfy the equation. The graph of an equation consists of all points whose coordinates satisfy the equation. The points correspond to solutions of the equation. I might call them solution points. So if I graph something in the Cartesian plane, then all the solution points on this graph will satisfy the equation of the graph, which will be ya equals ya. Okay? So that's the idea of the basic principle of graphing. Some of you might say, oh, that's obvious. But here's the deal. Later on, when we deal with polar coordinates in this class, or in 3 dimensions, if we're dealing with cylindrical or spherical coordinates, or for that matter, Cartesian coordinates in 3 dimensions, the basic principle of graphing will come in very, very handy. What's the graph of an equation? It consists of all points whose coordinates satisfy the equation. So if I ask you to graph an equation, I want you to plot all these solution points whose coordinates satisfy that equation. All right. Now, some very basic graphs are circles. And without even talking about X and Y, what is the locus definition of a circle? What is a purely geometric definition of a circle? This is called the locus definition of the circle, without even going to X and Y. All right, we begin with a fixed point, which is going to be the what of the circle? The center. And we want all points that are the same distance from the center. And I'm going to call that distance R. Why? Because R is going to be the what of the circle. I'll do this in blue. Do this in blue. R is going to be the what of the circle. R is going to be the radius of the circle. It's the distance between each point on the circle and this fixed point called the center. Bear in mind that twice the radius is called the diameter. Twice the radius is called the diameter. Now be careful, because the letter D might refer to specifically the diameter, or could represent a more generic distance. So be careful about the letter D. Know for sure what it means. Does it mean distance? Does it mean specifically a diameter? What is it? By the way, you can define a diameter as the length of the longest chord that can go through a circle. In fact, a diameter can be defined as the longest chord that goes through a circle. A chord is a line segment that connects 2 points on the circle as endpoints. 2 distinct endpoints. The diameter is the longest such chord that goes through a circle, and it has to go through the center. Okay, so that's the locus definition of a circle. Now, how can we get an equation of a circle in the xy plane? So in particular, if I want to consider the equation of a circle whose center is at the origin, 0, 0, in the xy plane, and whose radius is r for some positive length r. Remember, a radius has to be positive by definition. The radius is the distance between any point on the circle and the center. All right. Well, if I take a generic point, xy on the circle. First of all, how can I represent the distance between this generic point xy and the origin 0, 0? I can use the distance formula. And from the distance formula, what do we get? What's the distance between x, y and 0, 0? It's going to be the square root of x minus 0 all squared plus y minus 0 all squared. But of course, we don't have to have the minus zeros. So we can just say that the distance here, r, the radius, is given by the square root of x squared plus y squared. X squared plus y squared is the desired radius, the distance between a point xy on the circle and the origin 0, 0. So far, I have this as a proposed equation for the circle. I'll turn this around. I have the square root of x squared plus y squared equals r. You could say that that's an equation that represents this circle of radius r centered at the origin. But we don't like the square root over here, so we're going to square both sides. Now, I'll do this. On your homework and notes, try to be cleaner, but I'll just do this for now. Well, I'm going to square both sides. The square of r is r squared. All right. Now, when you take the square of a square root guy, what happens? You get the radicand, assuming that the radicand is non-negative. But the thing is, x squared plus y squared is guaranteed to be non-negative if x and y are real. If x is real, x squared is never negative. If y is real, y squared is never negative, and their sum can never be negative. That's good to know. X squared plus y squared can never be negative if x and y are real. But anyway, the square of the square root of x squared plus y squared, that's going to leave plain old x squared plus y squared, the radicand, equals r squared. Normally, when you square both sides of an equation, you have to do some checking. But we're going to be okay here, in part because of this, the fact that we know the radicand is non-negative. So the standard form for an equation of a circle like this, that has radius r and whose center is at the origin, the equation we use is x squared plus y squared equals r squared, where x squared plus y squared is the squared distance between x, y, and 0, 0. It's the square of the radius. So all the points on the circle, here have the property that their squared distance from the origin, x squared plus y squared, this is the squared distance from the origin, is going to be r squared, the square of the desired radius. X squared plus y squared equals r squared. That is, over here, x squared plus y squared equals r squared. That is, I need to write nicer ovals and circles. X squared plus y squared equals r squared is the standard form of the equation of a circle in the xy plane with center 0, 0, the origin, and radius r, where the radius r is positive. Okay, here's a much cleaner picture. This is the graph of x squared plus y squared equals r squared. According to the basic principle of graphing, this is the graph of this equation. The graph of an equation consists of all solution points x, y, whose coordinates satisfy this equation. This includes, for example, r, 0, where x equals r and y equals 0. Consider this equation, x squared plus y squared equals 9. Well, that's going to be a circle. The graph of this equation will be a circle with center at 0, 0, and the radius is not 9. 9 is r squared, remember. R squared is 9, so the radius r is 3. I know that 9 has 2 square roots, 3 and negative 3, but the radius is the non-negative root. All right, 3 meters, you could say. So here's the graph of the equation x squared plus y squared equals 9. How many points lie on this circle? How many solution points are there for this equation? Infinitely many. Infinitely many. But 4 of them are very obvious. 3, 0, 0, 3, negative 3, 0, and 0, negative 3. Those are the 4 most obvious ones. 3, 0 is a solution point. The point lies on the graph because 3 squared plus 0 squared equals 9. So the coordinates of the point will satisfy the equation. But it's not the only one. And these 4 compass points are not the only points that satisfy the equation. Consider this point over here. The point, well, how about over here? The point root 7, comma, root 2. The point root 7, comma, root 2. Is this a solution point? Well, do the coordinates satisfy this equation? X equals root 7. That's squared, plus y equals root 2. That's squared. Does that equal 9? Does that equal 9? Well, the square of root 7 is 7, plus the square of root 2 is 2. Yes, that does equal 9. 9 equals 9. That does check out. So root 7, comma, root 2 is a solution point for the circle, and it's a solution for this equation, where x is root 7 and y is root 2, this ordered pair. Don't discriminate against this point just because it has non-integer coefficients. Yes, the coordinates are irrational, but they are real. They do count. This circle has infinitely many solution points. And there are infinitely many distinct ordered pairs that satisfy this equation. By distinct, I mean different. Next up, what happens if we translate the circle so the center moves from 0, 0 to some other point, h, k? How do you translate a circle? Next time.